Okay, so first of all, good morning to you all. So from the previous class, we were discussing about the shear strength theory. So before we begin the today's class, if you have any questions, so I'm ready to clarify a few of them. So anybody has any question? Anybody has any question? Okay. So let us go ahead with the further discussion on the shear strength theory of a soil. So initially in the previous couple of classes, we tried to understood what is the cohesion and what is the angle of internal friction. So how these two affect the ultimate shear strength of the soil, so on and so forth. If you further discuss on, so how about the determination of a shear strength of a soil? So there are a few laboratory tests and there are a few field tests are available to determine the shear strength of a given soil. So let us try to discuss in detail about the various laboratory tests which are normally employed to determine the shear strength parameters. So those are C and pi value. So I don't need to re-emphasize what kind of the tests those are available, that everybody knows. Suppose if you want to list out, the very first one is you can go for direct shear test. So direct shear. So then UCS, unconfined compression test. So then UU. So then CU and CD. So these four are the triaxial tests, while the first one is direct shear test. So apart from this, so other different variety of tests are also available. For example, if you take the wave shear, so it can be conducted both in the laboratory as well as in the field. So this test is available both laboratory at field scale level. This test can be conducted. So apart from these tests, there are several other tests are available, so which are highly useful to determine the exact shear strength parameters of a soil. But when you talk about the shear strength parameters of a soil, so one common thing that you need to understand is, are you determining these shear strength parameters in their total form or effective stress form? Total stress form or effective stress form. So this is the most important thing, so that you need to understand. So what is the difference between the total stress forms or effective stress form? So suppose if you recall the fundamentals of the soil mechanics, so there you understood the total stress is nothing but, effective stress is nothing but total stress minus the pore water pressure. So, but what exactly is the meaning of this equation? What do you mean by the effective stress? What do you mean by the total stress? And what do you mean by the pore water pressure? So, anybody could give a logical clue? What is the physical meaning of sigma dash, sigma and U?
Sigma dash is the interparticle pressure, and U is the pore water pressure. That means when pore water pressure is developed, we consider it effective stress analysis. Like if it is a quick construction, then pore water pressure could not be developed. Then we will be having total stress analysis.
Okay. And what about the total?
Total stress is the addition of interparticle and pore water pressure stress.
Okay. So, if you exactly try to understand the physical meaning of all these three parameters, the total stress is nothing but the load bear by interparticles plus water component, interparticle plus water component. While when you talk about the U, the pore water, it indicates that it is the component of the load which is borne by the water only. While when you talk about the sigma dash, that is the effective stress, so it indicates that it is the load or the stress exclusively borne by the soil particles at the interparticle contact level. So if you look at this equation carefully, so the total, which is nothing but which encompasses both interparticle plus water, meaning thereby both soil particle and the water together bear the imposed stress or a load on the soil. But the problem comes is when you take this load borne by the soil and water together. So depending upon the presence of the water, so there is a reproportioning of the stress within the soil. The reason is the interparticle movement cannot happen the moment you apply the load. Whatever happens, normally we designate in the form of a compressibility or the consolidation. But if you compare the movement of the particle and the movement of the water, the moment you apply any load on the soil particle or on the soil mass, water cannot able to take any amount of the load. So therefore it tries to escape through the pores. Although initially it is able to bear a small fraction of the load, or it is suppose if you look at the theory of the consolidation, that is a spring analogy, where it is demonstrated that if no drainage valve is open, the entire load will be borne by only the water molecules. But there the condition is that so the water is not allowed to displace within a given controlled volume. But if you take a in general soil media, infinite soil media, such phenomenon will not happen. So there the enormous amount of the volume is available in all the directions that facilitates movement of the water in every direction. For example, for a small demonstration, I will take a small example. So this is a natural ground. So on which, suppose if you take a small element at any depth, so this is Z and any depth, so on which acting the axial stress and the confining pressure. So this is sigma V and this is sigma H. So this is very well known to you all. So this we can say the initial condition of the soil particle. So initial condition of the soil particle. Initial condition of the stress. Now what you do in the due course of the time, either you propose this site for the construction of the foundation or for the construction of the any superstructure. So let us assume that so on this soil particle, so there is a proposition of a construction of a foundation. So now you build a footing on top of this soil. So this is the ultimate load Q. Now as a result of construction of the footing, so if you look at the stress conditions on the element, although initially it was subjected to sigma H of the lateral stress and sigma V of the vertical stress, now due to the construction of the footing, there is an additional stress that comes into the picture, that is called as a delta sigma. Now this newly added delta sigma causes almost all kinds of changes in the engineering properties. For example, if you look at the consolidation equation, that is Cc into H divided by 1 plus E naught into so log sigma naught plus delta sigma divided by sigma naught. Now here the sigma naught is initial effective overburden stress, so before construction of any superstructure, while delta sigma is the increase in effective overburden pressure or increase in effective stress due to the construction of the superstructure. Now the consequence of the construction of this superstructure is it induces some kind of the compressibility or the consolidation within the soil mass. So as a result, you will get the settlement. So that is called as a SF. Now you can also understand, in absence of delta sigma, what would happen to this equation or the final settlement. Now in absence of the delta sigma, still the soil undergoes small amount of the consolidation, that is called as a self-weight consolidation. Or in general, otherwise, if you look at any consolidation theory, the final settlement is a result of the self-weight plus the imposed additional load. So here, so the imposed additional load is reflecting in the form of a settlement. Now the same thing, its reflection will also happens in the shear strength. In the shear strength, suppose if you look at, so the shear strength equation, tau is equal to C plus sigma tan pi. C plus sigma tan pi, where C and pi are the soil particle components and sigma is the imposed or whatever the normal load that is acting on that particular soil element. So this is how, so the shear strength increases as you progress the consolidation, or this is how we can correlate the consolidation with the shear strength. Now, to understand more intricately the interrelationship between the consolidation and shear strength, you need to have a fair understanding on the complete triaxial testing. Now let us take one by one. So first, let us try to assume about the UCS. So unconfined compressive strength test. So here what we do, or what is the fundamental meaning of this one? Suppose if I take any soil element, unconfined compressive strength, that means no confinement. But no confinement where? No confinement in the lateral direction. So no confinement in the lateral direction. So that is sigma 3 is 0 and there is a sigma 1 or the axial stress. So here the sample is allowed to fail only by increasing the axial stress without applying any amount of the confinement. That's why it is called as a unconfined compressive strength test. So sigma 3 is 0. Suppose if you ask to draw the Mohr circle, so for this one, so it is a single circle. Where, so we draw one horizontal line which represents Mohr Coulomb failure envelope. So this is Mohr Coulomb failure envelope. Since the line is a horizontal, there is no inclination, we don't have any angle of internal friction, and whatever the component that we get in the ordinate, that is called as a undrained cohesion of that particular soil. Undrained cohesion. While this is called as a undrained shear strength, we can say. Undrained cohesion or undrained shear strength. Why it is undrained?
Drainage is not allowed in here.
So drainage is not allowed. Or the other way around of understanding this one is, we are not allowing the water which exists in the soil sample to expel out from the soil sample. Okay. But we are also not providing the sigma 3. And another important thing is that when you do any UCS test, the application of the load is so rapid. So maybe within that short period of the time, there may not be any amount of the development of the pore water pressure. This can also be assumed. It may not be true in all the situations, but usually the application of the load is so rapid in case of the UCS. So this is what a small understanding about the unconfined compressive strength. So here only axial load is applied, the lateral load is almost 0. But this gives when there is no confinement. So this is contrary to the natural condition, because if you look at the realistic condition or the practical situation in the field, in the field. We cannot say that this sample shall not be subjected to the lateral stress, which is a little contrary. That's why UCS shall not be performed in each and every case. So UCS will give you only the least possible strength of a soil. It always gives least possible shear strength of a soil. It is only the qualitative value. So it is only the qualitative value. So it cannot be taken. But usually the UCS test is done on stabilized samples. Predominantly UCS tests are done on the stabilized soil samples in order to understand how much improvement in the soil strength. For that purpose it is dominantly used, but to determine the C value and pi value, we always must conduct either UU or CU or CD test. So these are the three fundamental tests which are made to determine the shear strength parameters of a soil. However, so it is up to you to decide whether you want to determine the shear strength of a soil either in total stress form or effective stress form. Okay, now how the total stress form and how the effective stress form parameters of the C and pi are determined, so that we will understand by taking the cases of one by one. Now first let us try to understand. So what is the fundamental distinction in UU, CU and CD? UU, CU and CD. So for example, here I am taking this small element or this small volume of the soil. So this is the small volume of the soil. Now initially when there was no footing, so this entire volume of the soil is subjected to only self-weight. But after the construction of this superstructure in the form of a footing, there is an additional stress that is delta sigma. While this additional stress causes consolidation of the soil volume, we can say approximately the soil volume is equals to your pressure bulb, because behind the pressure bulb the stress is zero. Within the pressure bulb only the stress exists. So that's what you understood from your earth pressure theories. Maybe if you look at your Westergaard theory or Bosnick's theory, so all those theories will be useful to establish what would be the total volume of the pressure bulb. Now within this controlled volume, what is happening to the soil state? For example, if I take the pure dry soil, assuming that there is no water, so what will happen to the shear strength parameters in a hypothetical condition? The pure dry soil, what kind of the stresses it could able to take, total or effective? And completely opposite is you take the saturated soil, completely saturated. So what is the difference between these two? The soil is dry and the soil is completely saturated.
For dry soil, there will be no pore water pressure.
Okay. So for dry soil, so the pore water pressure is zero. Okay. What about in saturated soil?
Sir, it will depend on if it is a quick construction or a gradual construction.
Okay. Is it quick construction or the gradual construction? But the basic thing is that the pore water pressure is not zero.
Yes.
Okay. Now, can I convert the saturated soil into the dry soil? So can it is possible to transform the saturated soil to the dry soil?
Practically, it isn't possible. 100% expulsion of water.
Okay. So may be possible, when you try to expel out the total water from the saturated soil. Okay, so that is a possibility. Meaning thereby, when you talk about the expulsion of the water from the saturated soil sample, what you are literally doing, you are playing with only the pore water pressure parameter. So initially, if the soil sample is fully saturated, the pore water pressure could be dominantly high. It could be as high as possible. While with time, what is happening? There is a prevalence of the consolidation because of the application of the delta sigma. Just imagine, because of this footing, because of this additional load, so the soil undergoes the consolidation. Now, as we know, if you look at the very fundamental meaning of the consolidation, it says that it is expulsion of the water from the pores or from the diffusion double layer. So basically, it is expulsion of the water. So now, as the water is getting expelled from the soil, we can presume that this volume initially when there was no load applied, prevalently it is in the state of unconsolidated undrained. Because no water is expelled out at that condition and no consolidation is also happening because there was no delta sigma. Now the moment we apply the delta sigma, there is a development of the pore water pressure, and this pore water pressure will try to dissipate with time, maybe over a period of 6 months or 1 year or 2 years or 5 years, other 10 years. Now with the expulsion of the water, there is a drastic reduction in the pore water pressure. So when there is a dissipation of the pore water pressure, there is a change in the state of the soil. That changes, if you look at this equation, so initially the soil in the total stress condition, as the water is getting expelled out from this controlled volume of the soil sample, the U component initially, which is very high, with a period of time, it slowly decreases. Now the consequence is that as U is decreasing, obviously the sigma dash is increasing. When sigma dash is increasing, you have already understood from the fundamentals of the soil mechanics. One of the reasons for consolidation is increase in the effective stress. So as I showed here. Now with the dissipation of the pore water pressure, so which creates some kind of the voids within the soil mass, because initially all the voids are occupied with the water. But as the water is getting dissipated or getting expelled from the same pore, so there is a readjustment of the particles that we call as a compressibility or the consolidation or the settlement, whatever it is. So that is the net reduction in the volume. Suppose if you talk in terms of the two-dimensional, we can say it is the consolidation. But if you take in three-dimensional, it is a net volume change because it is happening in all the 3 directions. That volume change is designated as the total consolidation. But if you take in the two-dimensional, it is the compressibility or the consolidation. Okay. So now, initially, so the soil within this controlled volume is in a state of unconsolidated undrained. As pore water pressure getting dissipated, the soil state changes as a result of the delta sigma from UU. So this is pore water pressure from UU to CU. So why CU? The moment you apply the load, the first phenomenon that takes place is the consolidation, not the failure. Consolidation. Okay. So consolidation, then followed by the failure. So therefore, the first phenomenon that is happening is consolidation. So from the unconsolidated, the soil is transformed to the consolidated. Now it is up to you. So whether you open the valve or not. In UU, the valve is not open, or in other way, from this controlled volume, no water is allowed to dissipate out of this bulb. That is called as a unconsolidated undrained. But with time, there is a dissipation or the expulsion of water from this small controlled volume, resulting the consolidation of the soil sample. That consolidation we measure as the settlement. So therefore consolidation and undrained. Here up to certain phase, or for example if you take any triaxial testing, there are two phases or two stages. So the stage 1 is the consolidation. Stage 1 is consolidation, while stage 2 is shearing. Stage 2 is shearing. Okay, shearing can happen only if the soil gets consolidated. Okay, which otherwise there is some other phenomenon. So even the fully saturated soil can collapse, but that may not be because of exactly shearing. Shearing predominantly happens following the consolidation process. So this you must understand very carefully. So the first stage 1, the first letter U or C is corresponding to the stage 1, while your second letter U is corresponding to the seeding stage. So during the seeding stage, if you allow the expulsion of the water, still consolidation happens. If you do not allow, the sample is unconsolidated. Now let us imagine that, so this node is for a longer period of time. Now in this control volume, we cannot say that the water getting not dissipated or not expelled out from that particular volume. Because if it is a triaxial testing, we are using the membranes and we have connected to the valves. Either you can close the valve or open the valve in the laboratory. So then we can say that it is consolidated or not consolidated, either during the consolidation phase or during the searing stage. But in practical condition, there is no such conditions exist, or these conditions are unnoticed basically. Unnoticed. But everything will happen. The moment you apply the load delta sigma, the first condition that prevails is the unconsolidated, undrained condition. Now, as the water is getting expelled from this controlled volume, then the soil condition transforms from UU to CU. And in the very long term, where due to the imposition of this delta sigma, the water is completely expelled out this from complete volume. In that condition, it again gets transformed from consolidated undrained to the consolidated drained. So at such stage, there was no water literally exists in that controlled volume of the soil sample. It is only the soil particles which are bearing the entire load. Now, another analogy that you need to understand is in CD or at the stage of the CD consolidated drain condition, the total the stress is replicated in the form of a effective stress where only the soil particles are bearing the entire load. Only the soil particles will bear the entire load. While in UU, majority of the load will be borne by the water component, while a fraction of the load will be borne by the soil particle, because it is undrained, unconsolidated. While in CU, so we can say, so majority of the load is borne by the soil and a fraction of the load is borne by the water. While when it comes to the CD, the entire load is borne by the soil particles only. Okay, and again, so this is only the basic understanding. But if you go the lot of intricate details, several assumptions and other things also you can understand. For example, if you look at the theory of the consolidation, that is spring analogy, the moment you apply the load, the instantaneously, the entire load will be borne by only the water at that instantaneous condition. And the amount of the load on the soil particle is zero. And that condition prevails until such time or until you are opening the valve. The same thing happens in case of the soil also. So, but at the very initial condition where the load is applied on the soil condition, so the pore water or the water tries to bear the entire load. But just imagine, when water is trying to bear the load, that condition is called as the pore water pressure development. Okay, at that condition called as this pore water pressure condition. pore water pressure. So this is the most important. However, this pore water pressure slowly gets dissipated because the movement of the water from the particular controlled volume. That means the pore water pressure initially is some very high value, but slowly gets dissipated. Okay, so this is what the short summary about the different triaxial testing in a nutshell. Now, you can also correlate this with the short-term and long-term strength of the soil also. For example, if anybody will ask, what are the practical applications of the UU, CU and CD? UU means it is the condition which is prevailing in the very short period of the time after application of the delta sigma. So therefore, UU normally applied in the short period of the time. While the opposite to is CD. But to arrive at the condition of the CD, it takes immense amount of a time. It's not a short term period, it's a long term period. See, long term period. So therefore, if you want to determine the shear strength of the soil in the short term, then you must consider the short term period. While if you want to determine the shear strength in the long term, then you must conduct the consolidated drain test, that is CD test. But which is the most critical? Although, we understand about all these things, but what is the most critical that causes failure in the soil sample? This is the point you need to understand. Because remaining all the things are available in the, if you refer to any soil mechanics book or the foundation engineering book, you will get plenty of information about the very fundamentals of UU, CU and CD. They say if you want a short-term strength, then conduct the UU. If you want long-term strength, then conduct the CD. But which is the most critical? Which causes the failure? So any idea? Is it the short-term loading or is it the long-term loading? So is it the condition with the water or is it the condition without the water? Which is the most critical and why?
Sir, when water decreases suddenly, sudden drawdown of water.
Okay, sudden drawdown of a water. Yeah. But what is happening there?
Sir, effective stress will increase suddenly.
Effective stress will increase suddenly. But if effective stress increment is there, then that is advantage, na? Effective stress means load borne by the soil particle only. So as long as the only particles are bearing the load, we are happy. There is no problem. That's more or less like a dry condition.
Sir,
Yeah.
sir, I have one question, sir. Effective stress and pore water pressure is acting downward or upward, sir?
Acting downward or upward? That depends upon the direction of the load that you are applying. We cannot generalize that.
Sir, suppose load is downward, so effective stress will be upward, na, sir?
No, there is no direction to particular thing. We cannot say this is in this direction or this is in direction. You have to understand at the particle level. These are manifestations of a gross phenomenon. So you cannot draw a simple free body diagram at the particle level and say that, so this is the particular direction of the total stress and effective stress. No. Suppose if you look at the sand boiling, so where It's a reverse completely. In case of the sand boiling, the stresses will come from the bottom of the sample to overcome the imposed or the overburden pressure. So that makes that neutralizes the effective stress.
Sir, having effective stress more is good or bad, sir?
That you have to tell me. See, having
Sir,
understood
I
this
think
much,
good, sir. Sir,
So
I think good, sir.
UU test will be the critical because
UU test will be the critical. Why? So why do you feel that it is a critical?
so I don't know the reason, but in the all the soil mechanics books, the formulas which are given, which are based on UU. For example, the cohesion which was given, which was CU given there.
Okay. Okay,
Sir,
that's true.
I think in UU test, uh, first, it, as you said, sir, it is a majority of the load is borne by the water only. So as the water is suddenly dissipated, that's why, sir, more settlement occurs, and that will be our failure condition.
Okay. Okay. So any other logical answers? Good. Good. So any other logical answer?
Sir,
Anybody?
sir, you have drawn more circle, but in that for what I mean sigma 3 will be 0, no, sir.
Yeah, sigma 3 will be 0. Yeah, it passes through origin. True. Yeah. So why the UU condition is critical? Others? Subhajit? Anasira?
Sir, since this is unconsolidated, I think there will be the effective stress will be less in this case. I mean, pore water pressure will be developed and effective stress will be less.
So more water will be developed and effective stress is less.
Yes.
Okay. Suppose, okay. Now, what will happen if the pore water pressure is developed too much? See, for example, I will take a small soil element.
Liquefaction.
No, liquefaction is a different phenomenon. Yeah. So,
Particle loses its cohesion, sir.
it loses its. Yeah. So you can somehow try to correlate in that aspect. So just imagine if there is too much of the pore water pressure inside the soil sample, it exerts the lateral thrust. It exerts the lateral thrust. But what we need completely opposite of to it. Say for example, when you apply the load, axial load, say sigma V or say sigma H, we always has to ensure that when I increase the load, either sigma H or delta sigma, and this load somehow some amount of the load is in fact you can say sigma V is equals to sigma H or sigma V is less than higher than the sigma H. But what we need to place the delta sigma parameter. Okay. Now, when you try to apply the delta sigma, so initially, depending upon the condition of the soil sample, say that is saturation level. Saturation level. If there is too much amount of water within the soil sample, so as we know, more is the water in the soil sample means more is the initial load borne by only that water particles. Okay. So more is the load borne by the water means it tries to exert the lateral thrust, or because it cannot able to dissipate immediately, because the dissipation of the pore water pressure is a time bound phenomenon. It won't happen like within 1 second or 1 minute or 1 hour. So it's a months and years of the phenomenon. So and again, so the permeability of the soil is very low. That part also you need to understand. Usually, another most important thing is that when you talk about all these total stress, effective stress, and the pore water pressure parameter, they are predominantly valid for the cohesive materials or the fine grained materials like silts and sands. Sorry, silts and clay material. I'm sorry, not sands. Okay, silts and clay material. But if you look at the permeability of the clay material, the permeability is very, very low. So in the order of 10 power minus 6 centimeter per second. 10 power minus 6 centimeter per second. So with such a very low permeability, you can anticipate or you can assess how much time it requires for water to get displaced from one location to another location. So it's an enormous amount of time, or you can say it's on a large scale basis. So significantly high amount of the time. But the load imposed is not very slow. We cannot say that today I will come and impose only 1 kg, and after 10 days or after say 1 month or 2 months, so I will again and come apply the load. So the load application will not go in such scale. The load application usually happens in a ramping mode. So it is not instantaneous. So rather, if you try to draw the diagram, so this is how it happens. So this is the time and this is the load. So it is applied in a ramping way. So constantly apply the load, but continuous. As the load is continuous, so there is a continuous increment in the pore water pressure also. But there is a threshold value up to which only the water able to bear the pressure. Thereafter it bursts. Okay. So that means as long as the water exists, which is normally implicated to a condition of the unconsolidated undrained. So that is the reason. The unconsolidated undrained condition becomes the critical. Because in that condition, the water exists, it tries to take the significant amount of the imposed load. Okay, that's why if you also look at the UU test, so we say this test replicates the end of the construction period. End of the construction period, which is the most critical. Why? By the end of the construction, you have already imposed maximum value of the delta sigma, or you attain to the state of application of the maximum delta sigma. But you did not literally play with sigma dash. There was no improvement in the sigma dash. Rather, there was improvement in the U value. So there was improvement in the U value. Whatever the load that is applied in the form of a delta sigma, whole load was borne by only the pore water pressure. So when this pore water pressure increases to certain threshold value, so it exerts the lateral thrust leading to the burst. So that's why it becomes the critical condition for or at the end of the construction. Now, once the construction is over, now what is happening? Your delta sigma is say post construction. Post construction. What is happening? Your delta sigma is constant. Your delta sigma is constant. Here, end of the construction, U is maximum. U is maximum. But post construction, with time, delta sigma is constant. But what is happening to U?
Continuously decreases.
Continuously decreases. Continuously decreases. So here it is continuously increases as we apply the load. But post construction, you are continuously decreasing the pore water pressure. Now just so try to put all these increment or decrement in the effective stress equation. So what is happening? Initially, with the application of the load, there is increase in the pore water pressure. But remaining other two stresses, so nothing is happening. But post construction, the U decreases, sigma increases. U decreases, sigma increases. Now, what do you mean by the sigma increment? That means the transformation of the load is happening from water now to the soil particles. The moment the water molecule gets dispelled, so who will share that load? Only soil particle has to share. So U decreases and sigma dash increases. So thereby, from unstable condition that prevails at the end of the construction period, you are moving to the stable condition where the soil particles are now trying to bear the majority amount of the load. But in between comes is the two states, that is U. So in this, C, not U. So in this state, the load is proportionately shared between water and the soil. But you can presume that, so in this state, majority of the load is borne by the soil particle and a fraction of the load is borne by the water. While ultimately, when U is becoming zero, the condition that it attains is called as a CD, consolidated drain. Okay, now is it clear? Okay, but when you do any kind of a stability analysis or when you do any kind of a settlement analysis or whatever you do it. Okay, say for example, when you are doing the stability, in stability, so the end of the construction is the critical, because pore water pressure is maximum, strength is least. Okay, why? So for consolidation, the maximum amount of water getting dispelled out at CD condition. That means the maximum amount of settlement can be anticipated only at the CD stage, not at the UU. Okay, so these are the few things that you must understand what is really happening and why such a condition is very critical. Why not other condition? Say for example, now you know the end of the construction. Once any structure is stable and safe at the end of the construction, it is obvious that for the remaining two stages also it is stable and safe, but need not to be ensured always. Anything can happen. Okay, that's why. So it is recommended to determine the stability and safety of any structure. So for all the three conditions, UU, CU and CD. But normally we take it for a grant. Once it is safe and stable against the end of the construction period, it is safe and stable at the CD period. Okay, this normally happens. But another important thing, say for example, this structure was built during the winter season. Just think of, okay, I'm giving one very classic example. Say for example, I built my footing during the winter, so where the groundwater table is at this location, at the footing location. Now with the application of the superstructure load, so there is some amount of the pressure that is developing on this controlled volume. So U is increasing and sigma dash is decreasing. While this is a continuous phenomenon, so the consolidation happens, the strength improvement occurs over a period of time. Say for example, the total time it took is 5 years. Over a period of 5 years of time, the total consolidation has happened. There was no development of the pore water pressure, so everything is fine. Now just imagine. So since the load is applied during the winter and there was no input of the water, so we can presume that so the entire water gets dispelled out from that particular location. But suppose what will happen during the next rainy season, or say after 5 years. Suppose if the again water level rises to the footing level. So as per our analogy, your shear strength should decrease. And again, you should arrive at the same initial condition at the time of the construction. But it is not happening so. Why? So during the construction, wherever the water
Can you
table is
please
there.
repeat, sir?
Okay.
My
So,
network got.
okay, I'm repeating the question. Say for example, at the initial phase of the construction, so the water table is almost at the footing level. Okay, you constructed and the soil got consolidated, everything is over. Okay, but by the next rainy season, again the water table rises to the same footing level because that is a natural phenomenon. Then what is happening to the strength? Will it be retained or will it be decreased? And what will happen to the pore water pressure also? Will it again regain to the initial value where at the end of the construction, or will it be lower?
It depends on the over consolidation ratio, no, sir?
Depends upon the over consolidation ratio. So how do you define the over consolidation ratio? How do you define it?
Effective stress in past. The effective stress in past divided by effective stress in present.
Effective stress in the past divided by effective stress in the
Present.
present. Okay. So how this OCR is going to impact your increment or decrement of U and sigma? Yeah, you have to speak. Please speak out. Because unless you understand all these fundamentals, so you're not able to apply all these fundamental concepts in reality. And you should also understand why all the concepts are like YCR, sigma dash, initial pore water pressure, final pore water pressure, all these things you have to understand. Unless you understand all these fundamentals, so you'll be having a tremendous amount of problem in applying these terminology for your practical problem. Okay, so just think of this situation. Okay, so maybe you can explain me in the next class.